a very nice and successful seminar and for inviting me to this talk. So today I'll be talking about the recent joint work with Yu Deng from the University of Southern California on the full derivation of the wave kinetic equation for analysis. So what we will be discussing today falls under the umbrella of something that's called Hilbert's sixth problem. And Hilbert's sixth problem essentially asks us to give axiomatic derivations of the laws of physics from first principles. So those first principles are typically, for example, Newton's laws or Hamilton's equations. And we would like to use those, take those as axioms and build on them in order to derive the other laws of physics. And the main example here is justifying, for example, the laws of statistical physics starting from the laws of dynamics. And as you all know, statistical laws govern macroscopic quantities, things like temperature, pressure, and fluid velocity. And these are typically time irreversible. So here, think of the second law of thermodynamics. Whereas the dynamical laws or our first principles, these govern microscopic quantities. Here we think of trajectories of particles, we think of an orbit of a dynamical system, and these are typically reversible in time. So here we think of Newton's laws and Hamilton's equations. And this passage, so the main problem comes from this passage from the reversible in time to the irreversible in time. And this comes as a result of an averaging and limiting operation of a series, possibly, of averaging and limiting operations, and this creates what is called an arrow of time. Okay, so and the problematic or Hilbert's sixth problem is essentially asked for a rigorous justification of this passage. Okay, so let me start with a classical example of this passage, which comes from Boltzmann's kinetic theory. So here, I believe this idea goes back to Hilbert, who suggested that the passage from the microscopic to the macroscopic should happen via an intermediate scale that's called the mesoscopic scale, and this is given by the kinetic theory. So let's give the example of Boltzmann's kinetic theory, which is arguably the most classical and most well-known example here. So suppose we start with a system of n particles, and think of those n particles as having radius r each, and they are undergoing elastic collisions, okay? And what we would like to do is we would like to derive an effective equation for the one particle density function. So this is what I denote here by Fn1. So here, what Fn1, you should think of it as the probability of finding a particle at position x moving at velocity v, okay? And what Boltzmann's theory tells us is that the effective dynamics of this one particle density function is given by the celebrated Boltzmann equation, which is given over here. I don't write it completely. The right-hand side is called the collision kernel. It's a bilinear operator. And so the justification of the approximation is the center problematic here. And this was a big challenge that was sort of first resolved by Lanford, but then investigated and completed, or the understanding is completed by several other works, particularly familiar to me, work of, particularly familiar is the work of Gallagher, Saint-Ramon, and Texier, which essentially closed in all the loops there and extended Lanford's result also considerably. Okay, so what does Lanfords theorem say? Roughly speaking, I want to go into the very precise statement, but it says that the Boltzmann equation over here appears as the effective equation for the one particle density function in the limit as the number of particles n goes to infinity and the radius of the particles goes to zero, but not arbitrarily. The n does not go to infinity arbitrarily, r does not go to zero arbitrarily. They approach their limits according to a scaling law, which will be an important theme for us later on, which is, so here this is the Boltzmann grad scaling law. So they approach their limits in such a way such that n times r to the d minus 1 is order of 1, stays order of 1, okay? So the approximation essentially says that the one particle density function converges or is approximated by f of t xv in the limit as n goes to infinity and r goes to 0 in this scaling law. Okay, and this holds up to times that are order of rho inverse. This is called the collision rate, and this the approximation, well, not holds, but it's proven up till now, or Lanfords Theorem reaches only those time scales. Okay, so, and this kinetic framework, while this was the first example of it, this has been highly informative and highly powerful in applications, and this was extended to many other particle systems. Okay. So what we would like to do today, or what we will be interested in today, is in Hilbert's sixth problem for wave systems. So having realized that waves are as fundamental objects as particles, 20th century physicists drew a parallel theory of statistical mechanics for nonlinear wave systems. So here, instead of thinking of particles that are undergoing Newtonian motion, the microscopic dynamics is given by a nonlinear dispersive PD. Okay, so and instead of the large number of particles, we will think of a large number of waves, and those waves are modeled by the Fourier modes of the solution for the nonlinear dispersive PDE. And thus, this nonlinear dispersive PDE is posed on a large box of size L, and L will be going to infinity. So this L going to infinity will become, in a way, the analog of capital N, the number of particles going to infinity. Because as L goes to infinity, the number of waves that are sustained in such a box also goes to infinity, or the number of effective waves that in this box goes to infinity as well. Okay, and instead of the collisions here, the waves undergo nonlinear interactions, and these nonlinear interactions are dictated by the dispersive system. Okay, so instead of Newton's laws, we have now a Hamiltonian dispersive PDE to govern the nonlinear wave interactions. So we'll take the simplest non-trivial case for us, which is the nonlinear Schrodinger equation stated over here. I dt plus Laplacian V is equal to V squared V. And we'll pose this equation on a box of size L with periodic boundary conditions. Okay, so we will denote this box as TD sub L. So this TD sub L, the shape of the box, we can it can vary. So, or the aspect ratios of the box can vary. So this TD sub L is we take it as L into a dilation of the unit box 0 gamma 1 up to 0 gamma d, where those gamma 1 up to gamma d tell you information about the shape of the box. We say that this torus is rational if gamma 1 up to, or let's say, let me define what needs to be irrational. We say that the torus is irrational if gamma 1 up to gamma d are rationally independent, which means that k dot gamma is different from 0 and k is not 0. And also we say that it is generically irrational if, in addition to this condition, the gamma satisfy a Diophantine condition. That is a generic Diophantine condition. Okay, so this is the equation that we'll be dealing with, and the aim of the statistical theory is to give an understanding of the long time behavior of the equation. Now, a deterministic understanding of the long time behavior is practically impossible, and the reason for that is the very rich set of possible long time behaviors that can be sustained by this equation. For example, you have periodic solutions, you have solutions that are quasi-periodic, possibly almost periodic solutions, soliton-like behaviors. So there's a lot of long-time behaviors that can be sustained by solutions. And even on RD, even in cases where we might have a good understanding of the asymptotic behavior of solutions. For example, if we are in a situation where the equation scatters, we know that all solutions scatter as t goes to infinity. In some sense, the intermediate time behavior, before those solutions start scattering, is not something that is well understood. Okay, so even in those cases, a statistical approach is needed. Okay, in order to understand the behavior of generic solutions. So before we continue with describing what this statistical theory says, we need to understand the parameters of the problem. We've already encountered one parameter, which is the size L of the box. The second parameter is the characteristic size lambda of the solutions. Okay, so in order to emphasize this size lambda of the solutions, we'll adopt the ansatz V equals lambda U, and think of U as having, say, unit size in L2, for example. Okay, and then in that case, the equation satisfied by U is exactly the same equation satisfied by V, except that you add a lambda squared in front of the nonlinearity. So here I did also a rescaling in a rescaled space, so that I would be working on the square torus of size L, but this comes at the expense, after we rescale, this comes at the expense of changing the Laplacian a little bit, so that instead of the usual Laplacian, I rescale it, or I twist it by factors beta 1 up to beta sub d, which are, of course, related to the gamma 1 up to gamma sub d on the previous slide. Okay? And the square torus so corresponds to the cases when beta 1 up to beta d is equal to 1. Okay, so it turns out that it is more convenient to state the results, or to even understand the results, not in terms of the size of the characteristic size of the solutions, but in terms of the characteristic size of the nonlinearity. So we introduced this dependent parameter, if you like, this parameter alpha, which is lambda squared over L to the D. And this, we will think of it as the characteristic size of the nonlinearity. So instead of having lambda and L as as the two important parameters, we will instead replace lambda by alpha. Okay, the results become a little bit easier to state. Okay, why is this? Why do I call it the characteristic size of the nonlinearity? We can justify it heuristically here. And of course, it is justified in a more rigorous way in the proof. And what heuristically, why is alpha the generic or the characteristic size of the nonlinearity? It is because if you pick a random L2 normalized function, okay, on a torus of size L, then generically this will have L infinity norm that is order of L to the minus d over 2, or with very high probability, it will have an L infinity norm that is order of L to the d minus 2. So in other words, it's sort of uniformly distributed. It's not, doesn't have too many spikes. And as such, if I measure the size of the nonlinearity in L2, I put one copy of U in L2 and two copies in L infinity. And as a result, I get that it is at least here upper bounded by alpha, but it actually is also order of alpha in general. Again, this is a heuristic argument just to justify why am I calling this parameter the characteristic size of the nonlinearity. But again, as I said, it is something that can be justified rigorously, and it is as part of the proof. Okay, so what about the initial data? So we started, remember, we are starting with NLS, this NLS equation over here, okay? And the initial data, just as in the many particle setting, we will start with a random distribution of the initial data. And this corresponds to us taking random independent Fourier modes for the initial data of the nonlinear Schrodinger equation, which we call the U initial. So U initial, this is just its expansion in Fourier space. Okay, so here K, so here U hat at K is the Fourier transform, and K, since you are working on a torus of size L, K ranges on a lattice which has mesh L inverse. Okay, so this lattice is nothing but L inverse ZD. Okay, and the random independent Fourier modes this is included in this statement over here. So we take the initial data, or the Fourier transform of the initial data, as follows. So the Fourier transform at K, it is given by the square root of n initial. N initial is a Schwartz function, and it will serve as the initial data for our kinetic equation later on. So multiplied by eta k, which are random variables. So these eta k's are IID normalized Gaussian random variables. And in such a way, what we have that the expected value of the Fourier transform squared of the initial data is given by the function n initial of k. When this is satisfied, we call such data well prepared, okay? Because this sort of prepares us adequately in order to approximate the NLS dynamics later on with the dynamics of the kinetic equation. Okay, so in other words, the goal of the kinetic theory is to understand the distribution of the Fourier modes at later times. Okay, and the central quantity is the expected value of u hat of tk squared. Okay, of course, this is sort of, in some sense, this is the Fourier transform of a covariance function in physical space, but let's not go into that. So this is the central quantity. It's the expected value of u hat of tk squared, and we would like to get an effective equation for this quantity. And the initial data was well prepared in such a way such that the expected value of the initial data squared in Fourier space is given by an initial of k, which is a Schwartz function, and this would serve as the initial data for the wave kinetic equation. Okay, so the kinetic dynamics appear in the limit when L goes to infinity and alpha goes to 0. And this is what replaces the limits n goes to infinity and r goes to 0 in Boltzmann's particle theory. Okay, any questions for now? Okay, so what does this wave kinetic theory, or which is also called wave turbulence theory, by the way, what does it say? So the big conjecture here is that in the limit as L goes to infinity and alpha goes to 0, so of course alpha is the strength of the nonlinearity, so it going to 0 is an indication of a weak nonlinearity setting. What it says is that the effective dynamics of the expected value of the Fourier amplitude squared u hat of tk squared. So this is the solution of the NLS equation at time t. We take its Fourier transform, we get u hat of tk squared. This is given by the wave kinetic equation, which I will state on the next slide. Okay, so rescaled up to the kinetic time, which is alpha to the -2. Okay, so namely, more precisely, what this says is that the expected value of u hat of tk squared should be equal to the solution of the wave kinetic equation at time t, rescaled appropriately. So this is n of t over t kinetic at k plus an error. Okay, and this error goes to 0 as L goes to infinity and alpha goes to 0. Okay, so here n of tc is a solution of the wave kinetic equation with initial data n initial, and u of t solves NLS with well-prepared data u initial. Okay, so that's the kinetic conjecture. So now of course I owe you the statement of what this wave kinetic equation looks like. And so this equation was derived formally in the physics literature in the past century, and it has the following form. It has the form dTn equals to k of n. So this is a trilinear operator, and its initial data is n initial, where k of n is given by the following expression. You can think of this as the collision kernel in this setting. Okay, so it's an integral over xc1 minus xc2 plus xc3 is equal to xc. So if you're measuring k of n at xc, you integrate in xc1, xc2, and xc3 on such that xc1 minus xc2 plus xc3 is equal to xc. But not only that, you also integrate on this variety, which is xc1 squared minus xc2 squared plus xc3 squared minus xc squared. Okay, and here you have, and this is the integrand, which is given over here. All right. So here I should mention that something I should have written is C1. When I write, say, x beta squared, we mean by this is beta 1 x1 squared plus beta 2 x2 squared plus ... beta sub d xd squared. Okay. So this is the wave analog of Boltzmann's equation. Okay, this is how this equation is understood. And again, this kinetic approximation features a passage from the time reversible nonlinear Schrodinger equation into the time irreversible wave kinetic equation. Okay, and one can also study the inhomogeneous versions of this equation. So in which case n depends on x in addition to c, and you would have a transport term here. That is called the inhomogeneous version, the inhomogeneous setting. Here we are sticking to the homogeneous setting, which seems to be of great interest in general. Okay, so let me say a few words about the physics background here. So the emergence of wave turbulence theory was in the 1920s. The first work is the work of Peierls for anharmonic crystals. And since then, this kinetic formalism was generalized to many nonlinear wave systems. For example, in the context of water waves, the kinetic equation is called Hasselmann's equation. And for example, in the context of anharmonic crystals, it's called the Boltzmann equation. And there are many wave kinetic equations in the context of plasma theory. And it's highly informative in applications in oceanography, optics, etc. But most notably, it is one important reason why this is such a interesting theory is that it leads to a formal framework of turbulence for nonlinear waves. And this is why this is called wave turbulence theory. This theory is called wave turbulence theory. Indeed, this formalism comes so this formalism is the analog of the formalism, if you like, of hydrodynamic turbulence in terms of the appearance of power law cascade spectra, like in Kolmogorov's 41 theory. And these spectra appear as special stationary solutions of the wave kinetic equation, okay? And those were discovered by Zakharov in the 60s, and I refer you to the manuscript by Nazarenko if you want more information about that. We won't be going into those solutions today. Okay, but there's also those solutions have been investigated in a rigorous setting as solutions of the wave kinetic equation by Escobedo, Velasquez, Sofer-Tran, and others. Okay, so okay, so there's influenced by this. There's a whole field of physics, as I said, that is interested in such questions and influenced by this field, particularly influenced by those solutions of Zakharov. The initial focus of the mathematical research was on constructing solutions for the nonlinear Schrodinger equation that exhibited growth of Sobolev norms, or this growth of Sobolev norms is related to the cascade of energy from low to high frequencies. Okay, so this is a growth of Sobolev norm is an implication of a cascade of energy from low to high frequencies, and this is something that is implied by those power law solutions. Okay, and it is predicted as said here by the Kolmogorov-Zakharov spectra. So here are the pioneering people were Bourgain, Stafilani, and probably the most influential work here is the work of Colliander, Kiel, Quoc-Hung, and Tau, who constructed solutions that exhibited large but finite growth of Sobolev norms. And then many other people also contributed to this line of research. But the central question here remains is to give a rigorous justification of this kinetic approximation, like this, what we called approx a couple slides before. So can we justify this thing? Can we prove this rigorously? That's really the central question for us today. And mathematically, this is a question that has both importance from a mathematical perspective and also from a physical perspective. From a mathematical perspective, of course, this gives you a very important insight into generic long-time behavior of solutions of NLS, including questions related to energy cascade and growth of Sobolev norms. But also it's important physically in order or justifying proving this approximation rigorously is important for the physical theory because it allows us to understand the exact regimes and limitations of wave turbulence. Actually, indeed, this was a question that was posed by physicists to mathematicians to put this justification on rigorous mathematical framework. In terms of previous work, there are a few related works to this question. Most notably, there's a very nice work of Lucarin and Spohn that studies a discrete NLS at an equilibrium setting and asks related and answers related questions to this justification. There are also some partial results by Pfau. I only mentioned Pfau, Dymov, and Kuxin, and there are others. For example, in Pfau's work, there's a justification of a linearized version of the kinetic equation. And Dymov and Kuxin, they consider an equation with some forcing, and they give also some partial results there. But the first attempt at the full problem, first attempt at justifying this approximation here was in the work of Buckmaster, Germain, myself, and Chata a couple of years ago. And there, in the setting of generic tori in dimension d greater or equal to 3, we justified the approximation, but only to times that are way shorter than the kinetic timescale. We justify this approximation for times that are much, much smaller than the kinetic timescale, some like positive power of L smaller, something like L to the minus alpha T kinetic, okay? The importance of, or part of the importance of that work is that also resolved all the sort of number theoretic issues that could arise in the setting of generic irrational tori for this particular problem. Later works after this initial work of Buckmaster, Germain, myself, and Chata, later works by Yu Deng and myself, and also by Charles Collot and Germain, improved this approximation interval considerably. I will talk more precisely what those later works say in a couple of slides. And the reason for that is that those two works emphasize the importance of scaling law in this problem. So just like the Boltzmann grad scaling law was important to be imposed for the Boltzmann theory, those two works sort of or put the spotlight on the needed spotlight on the scaling law in the derivation of the wave kinetic equation. So let me talk a little bit about scaling laws, and then I will come back and discuss in more detail what those two results did. Okay, so scaling laws, again, we've already encountered an example of a scaling law, which is the Boltzmann grad scaling law, when we impose that n r to the d minus 1 is order of 1. So essentially, a scaling law dictates the relative rates of the limits L goes to infinity and alpha goes to 0. Okay, and a priori, you might think, okay, let me start by considering all possible scaling laws of the form alpha equals L to the minus gamma, where gamma could be anything, could be 0, could be infinity, or anything in between. The case gamma equals 0 can be understood as taking the limit L goes to infinity first, and then taking the limit alpha goes to 0, and vice versa for the case gamma equals infinity. However, it's not very hard to justify, and it's not very hard to see that not all those scaling laws are admissible by the kinetic theory. Okay, it turns out, and the admissible scaling law depend a little bit on the shape of the torus or the shape of the domain. For example, whether you're working on a rational or irrational torus. It turns out that for general tori, without any genericity assumption on the tori, so if you're talking about whether your torus is rational or irrational, the only admissible scaling laws are the scaling laws gamma between 0 and 1. So for example, in the case of the rational torus, these are the only admissible scaling laws. Okay, and if you impose genericity assumptions on your torus, the admissible scaling laws that give you a kinetic approximation widens a little bit from 0 to 1 to up to 0 to d over 2. Okay, and it seems that the interest in one scaling law over the other might depend on the physical context. Okay, so now we can go back and explain more precisely what the results in 2019 looked like. So in our 2019 work with Yu Deng, we proved the approximations up to times that are almost reach the kinetic timescale, but not quite. They are L to the minus epsilon times the kinetic timescale. And this L to the minus epsilon makes a huge difference, as we will discuss later. Okay, and we were able to reach this time scale for two favorable scaling laws corresponding to gamma equals 1 and gamma equals epsilon in a way. Okay, and we also we had some partial results for the other scaling laws, what would happen, and some counter examples that might complicate things in the case for the other scaling laws. And around the same time as our work with Yu Deng, there was a work of Collot and Germain, which essentially proved the same result. So they got to this almost the kinetic time scale and the scaling below gamma equals 1. And then there was a very nice follow-up work by also Collot and Germain in 2020, where they studied the problem on even non-rectangular tori, and they studied an existence question that is important for the derivation of the wave kinetic theory over there as well. Okay, so of course, the drawback of all those results is that they don't reach the kinetic timescale T kinetic, which is the timescale at which we start observing the dynamics of the wave kinetic equation. And so this is what we give a distinction between this full justification of the equation. So a full justification of the equation should reach times that are multiples of the kinetic timescale, okay, where delta is independent of the asymptotic parameters L and F. Delta is just a fixed universal constant, if you like, or fixed constant independent of L and F. So this brings us to the main result of today. This is a very recent joint work with Yu Deng, and in which we're able to give a full derivation of the wave kinetic equation from NLS. So the theorem can be stated as follows. So consider the NLS equation on the torus TD in dimensions greater than or equal to 3 and with generic choice of beta. We assume that the initial data this is the initial data for the wave kinetic equation, is a Schwartz function. Of course, this is an overkill. We only need finitely many Schwartz norms, but we don't try to optimize that. And we take the initial data for NLS to be well prepared, so that the expected value at time t equals to 0, the approximation holds. That's what well prepared is. Okay, so here this is the scaling law. We adopt the scaling law alpha equals L to the minus 1. So this is the scaling law gamma equals 1 that was mentioned in the previous slide. This was one of the favorable scaling laws that was identified in our previous work. And the kinetic timescale is, as always, alpha to the minus 2. Then the theorem says that there exists delta that is fixed, less than 1, and an absolute constant nu, such that if L is large enough, you have the needed approximation. You approximate the expected value of u hat of tk squared by the solution of the wave kinetic equation, rescaled as t over t kinetic, plus something that goes to 0 as L goes to infinity. And actually goes to 0 like L to the minus nu for some positive. Okay, and this statement holds uniformly in t and k, and this is the key point, that t now reaches a multiple delta, which is delta times the kinetic timescale. Okay, of course, n of tk is the solution of the wave kinetic equation with the initial data and initial. Okay. So this is the main theorem for today. Okay, so let's have some remarks on the results. So this is the first result of its kind on for any nonlinear dispersive system. So while we stated this result in the particular scaling law alpha equals L inverse for definiteness, actually the same proof extends to scaling laws of the form L to the minus gamma, provided gamma is smaller but close to 1. And in such, so this is an important remark actually, for such scaling laws that we don't need any genericity assumption on the shape of the domain. Okay? Yeah, so there's no need for a genericity assumption on the shape domain for those scaling laws. Whenever you get to L to the alpha equals L to the minus gamma, or gamma is less than 1, there's no need for the genericity assumptions, and this is the case. We plan to study, as I said, our proof extends directly to the case when gamma is close enough to 1, but we plan to study the general scaling laws where gamma is between 0 and 1 in a future work. Okay, so why the scaling law alpha equals L inverse? This carries a particular mathematical importance because of the way the result scales back to the unit torus. So remember, the kinetic time scale is alpha to the minus 2, which is L squared in this setting. Okay, and as a result, we're working on a torus of size L at time scales that are order of L to the minus 2. This means that you can rescale back to the unit torus. So this rescale back to unit torus and get results about dynamics of times order of 1. Okay, so in particular, we obtain dynamics for the Littlewood-Paley projections of the Gibbs measure in 3D. And this links our theorem to the still open problem of the invariance of the Gibbs measure for the 3D cubic NLS. This is the only remaining unsolved Gibbs measure problem after the those very important recent works of Deng, Nahmod, and Yu, who essentially closed all the other Gibbs measure problems. And this is the only remaining one for which the Gibbs measure exists, but the invariance is still not proven. And the common difficulty between our problem and this invariance of Gibbs measure problem in 3D, the common difficulty is that they are both probabilistically critical problems. And we will I will explain what this means, and we will discuss it in a couple of slides. Now, prior to this work, there's no results existed on probabilistic critical problem, including in the parabolic set. Okay, I'll define it, and we'll come back to this discussion later on. Okay, so the proof is rather elaborate and long, so I will only have time to give a very high-level overview of the proof, or somewhat of a philosophical overview of the proof, if you like. So the basic starting point in the proof is to perform a power series expansion of the solution. So you write your solution mu as the sum of its Picard iterates plus a remainder. So U0 is the first Picard iterate, which is essentially nothing but e to the it Laplace U initial. And then U1 is the first iterate, UN is the nth iterate. Each of those UNs are multilinear Gaussian expressions, because each UN depends only on the initial data. They are iterates. They depend only on the initial data, and the initial data were given in Fourier space by independent Gaussians, essentially. Okay, and they can be represented by trees with n branching nodes. So let me give some examples here. So if I'm looking at the first or the zeroth iterate, we said it is it Laplacian U initial. Okay, so this thing we represented by a single node. Okay, and in Fourier space, so if I look at the Fourier transform of UN, so this is single node along with a k next to it. Okay, we call this a decorated. So this is a trivial tree. This is a decorated tree. Okay, let's just look at the first iterate. So U1. U1 is essentially, so this is, I denote by I the Duhamel operator. So it's just I of U0, U0, U0. And this is represented by a tree with one branching node, which is the root of the tree over here. And in terms of in Fourier space, this would correspond to having a decoration where I put k here, because I'm looking at the Fourier transform of this thing at k. And then I have k1, k2, k3 at each of the nodes over here, such that k is equal to k1 minus k2 plus k3. Okay. K1. Okay, and this comes from just taking the Fourier transform of this iterate. So let's try to do an example of U2. So this would be I of U1, U0, U0, for example, plus similar terms where you replace U1 here and or you put it here. Okay, so in that case, the tree would look like this. You branch from the first root. So this is a tree with two branching nodes. So scale of this tree is equal to 2. The scale of the tree is the number of branching nodes. And in terms of the decoration, you have, this is K, this would be K1, K2, K3, and this would be, say, N1, N2, N3. And again, at each branching nodes, you have that K1 is equal to N1 minus N2 plus N3. And at this branching node, you also have this to be satisfied. So that's how we represent the iterates. And in general, you have the iterates up to n. You represent those iterates as a sum over ternary trees, a sum of, if you like, of ternary trees and decorations on those ternary trees. Okay, so that's how we go from those iterates to the tree expression. So this is what we're saying over here. U hat can be represented as a sum of decorated trees, with the Fourier transform being the sum over all decorated trees or decorated ternary trees of scale n. Okay, and as a result, now that I have an expression of U hat in terms of the decorated trees, I have an expression of the central quantity that I want to find, which is expected value of U hat of tk squared. So this thing over here, this is the expected value of U hat of tk. u hat bar of tk. Okay, so express this as sum of trees. This is sum of trees, and as a result, this expected value of u hat of tk squared will be expressed as the sums of couples of trees. Okay, so we call those paired couples of trees, and those trees look. So this is an example of a couple of trees. So this might be coming from. This is coming from here. This is coming from the expansion of this. And the key point is that the leaves of those trees are paired to each other. And the reason why those leaves are paired to each other because of Kirchhoff rules that dictate, because we have chosen independent Fourier modes. Okay, so for example, here the pairing between leaves is denoted by having the same color. Okay, so this is paired to this is paired to this, the yellow ones and paired to each other, etc. Okay, and these are two decorated trees that are paired to each other. And of course, if you have two nodes that are paired to each other, you have to assign the same frequency to them. Okay. All right, so this is how we express the expected value of u hat of tk as a sum over couples. Okay, and there are two enemies to overcome in this problem. The first enemy is that there are order of n factorial couples that have scale n. Okay, n is the total number of branching nodes in the couple. Okay, this represents a major obstruction and to prove convergence of a power series expansion. So here the toy problem or the silly examples, if you have a power series a n t to the n, and if this a n grows factorially, then the radius of convergence of this power series is 0. Okay, so this is factorial divergences are always a big problem when you're dealing with convergence of power series. The second enemy is the criticality of the problem that was mentioned before. It's the fact that the iterate un plus 1 is only better than un by a factor of delta. It's not better than un by a factor of L to the minus epsilon. Okay, so we'll discuss. Let us start with the second enemy and see how it reflects itself on the problem. So this is the criticality of the problem. This is the manifestation of the criticality of the problem. In fact, the kinetic time scale can be understood as the longest time scale for which the power series expansion is valid. Okay, why is this so? Let us go back to our previous work in 2019. You can think of this as the subcritical version of this problem that we are discussing today. So here we treated in that work, we treated the full subcritical regime, t less than L to the minus epsilon times the kinetic time scale. And in that setting, un plus 1 is better than un only by a factor, well, not only, but by a factor of L to the minus epsilon, which is great. And the reason why this is great is that this tells you that you might expect or you might hope that the estimate for un to be order of L to the minus epsilon capital N, which means that you only need to do a finite expansion, a possibly very long, but finite expansion, where you expand up to capital N being order of epsilon inverse, okay, in order to prove the approximation. And in that work, we did estimate this long but finite expansion by exploiting some subtle combinatorial structure of trees. It's highly non-trivial, but it still can be done, okay? So in our critical setting here, unfortunately, the best thing we can hope for un is to have an estimate order of delta to the n, because as we said, un plus 1 is better than un only by a factor of delta. So the nth iterate, the best version or the best case scenario to have an estimate is order of delta to the n for a typical typical candidate of this nth iterate. Okay, and for this to be an error, we need, or for this delta to the n to be less than L to the minus nu, we need to pick n to be something that grows like log L as L goes to infinity. In other words, we need to deal with an expansion that as L goes to infinity, this expansion becomes infinite. Okay, so this is the difficulty that is imposed by the criticality of the problem. Okay, so let me talk about the second enemy, which is the factorial divergence. And in some sense, it's really the main enemy here. So recall that when we expanded the u hat of tk squared, for example, when I expanded the nth iterate, the expected value of the nth iterate square or the variance of the nth iterate, this becomes a sum of essentially 2n factorial couples. There are 2n factorial couples that contribute to the expected value of un squared. And if those, we know that some of those couples have size delta to the n. We can write it down. We know that some of those couples have size delta to the n. Now, if all those couples have size delta to the n, we are doomed to fail. We're dead. Okay, because we get that the coefficients of our power series an to the n grow factorial. But one might ask a question which will provide a strategy for us to attack the problem later on. And the question is, can we classify those couples into groups such that those groups that saturate or almost saturate the worst case estimate, which is delta to the n, are actually few. They're not so many. Okay. For example, we allow them to be, and they are, exponential in n, but they're not factorial in n. That's the key point. We allow things to be exponential in n, but we do not allow them to be, or actually there aren't a factorial number of them. So, this is the central strategy. So, can we divide those couples into groups such that the worst case estimates, the group which has worst case estimates, is not factorial in n, maybe exponential in n, but the remaining couples, which are factorial in many, satisfy considerably better estimates than the worst case scenario. For example, they can feature a power gain in L that would be sufficient to offset the factorial loss. Okay, so that's the strategy that we adopt. Of course, I mean, our first computations, when we start working on the problem, we were hoping, or the hope is that the couples that give you the worst case estimates are exactly the couples that converge to the iterates of the wave kinetic equation. They are exactly the couples that give you the wave kinetic equation, and everything else can be treated as an error. Okay, so you would hope that the couples that almost saturate the estimates are the leading ones that converge to the wave kinetic equation. Unfortunately, life is not so simple as such. There are more than there are the couples that saturate or almost saturate the estimates. They are not only the couples that give you the wave kinetic equation. It turns out that we identify 3 families of couples that have almost saturated estimates. So the first family is what we call the regular couples, and these are essentially the couples that converge to the wave kinetic equation. This is again a small lie because there's some plus there are some of those couples that actually do not converge to the wave kinetic equation, but luckily they converge to 0 in the limit, or they cancel out. The second family, which also has saturated or almost saturated estimates, is what we call irregular chains. Okay, and these lead to almost saturated estimates. But the good thing about them is that they feature a major cancellation, which makes them less important, makes them in some sense vanish in the limit. Now, the third family of couples, which again has almost saturated estimates, are what we call type 2 molecular chains. Unfortunately, I don't have time to describe those enemies to you if you like. So these are type 2 molecular chains, but again, while they have almost saturated estimates, they satisfy a favorable L1 in time bound, which makes their contribution acceptable. Okay. So what about the remaining ones? So the good news is that while there are those 3 families of couples that lead to almost saturated estimate, the good news is that there are only C to the n of such families. So you're still not doomed. Okay. So whereas the remaining, so you can still hope, and this turns out to be true, that the remaining number of couples, the factorial in n couples, feature a gain in n. This is the content of our main rigidity theorem, which is arguably the most important theorem in our work. What does this rigidity theorem say? It says the following. It says that if you take a couple, a very large couple, and you perform a type of surgery on this couple in such a way that this surgery removes all those things from the couple, okay? All those instances of those things. So it removes from it the subcouples that are regular. It removes from it subcouples that look like irregular chains and subcouples that look like type 2 molecular chains. This can be done by some sophisticated combinatorics. Okay, then we are left with a reduced couple or reduced structure whose estimate features a gain of L to the minus R, where R is comparable to the size of this structure. So R is the size of the couple after we remove those three enemies, the regular couples, the irregular chains, and the type 2 chains. After we remove them, we're left with a couple of size R, and the rigidity theorems that the estimate for such a couples has a gain of L to the minus a constant times R, minus CR. Okay. Now the number of possibilities of such structures that we obtain is R factorial. It's still factorial, but we have a gain of L to the minus R that is accompanied with this. So this gain L to the minus R is sufficient to offset this R factorial gain, because L to the minus R, I can make it less than L to the minus nu, provided R is less than a logarithm enough, which it is. Because remember, I picked my capital N to be essentially logarithmic enough. Okay, so this gain L to the minus R is sufficient enough, or is large enough, in order to offset the factorial divergence that is coming from the possibilities of, or the number of those couples. Okay, and of course the proof of this rigidity theorem is quite sophisticated, and it involves recasting the problem of counting the couples into counting another family of combinatorial structures that we call molecules. And the way we count those molecules is by running some sort of a computer program to reduce and count those molecules effectively. So let me give you a very quick example of such molecules. So this is a couple, the couple that appeared a couple slides before, and this is the molecule associated to it. So remember, a couple is decorated by those frequencies or the Fourier modes, k, such that you have L minus E plus M is equal to K, etc. And the same thing holds at every branching node. So you can recast this in terms of a combinatorial problem with the molecules instead. The advantage of this picture is that it makes the pairing relation a local relation rather than it being a non-local relation. So at the level of the trees, you can have this mode paired with a very, very far away mode in the tree. But this picture at the level of the molecules makes it local. I have to credit my collaborator Yu Deng for coming up with this very nice idea, which really was very helpful and very important to us. Okay, so the analysis of the couple of families mentioned above, yes. So I was very quick in telling you that we have those families of couples, the regular couples, the irregular chain, the type 2 chains. Each one of those enemies, or what I called enemies, each one of those requires a different type of argument in order to deal with it. And those arguments are, some of them are combinatorial constructions, some are analytic ones, and some are number theoretic ones, as is usual in the past few words on this topic. And once this picture is made clear, I mean, this tells you, I have told you how to deal with the iterates. The estimate on the remainder is relatively easier and can be derived from the analysis above. It turns out that it's a subsequence of the analysis above. Okay, so that's all I have for today. I want to thank you for your attention, and